Okay, so we'll continue on our discussion on matrices. I'm just sharing the screen. Hmm. Good evening. So, the last class we discussed the properties of operations on matrices, that is, properties related to addition and multiplication, and a few problems also we solved. So, now another very important operation today we'll discuss, that is transpose of a matrix. So this is one of the operations on the matrix. So when you say transpose, it means so if definition, transpose of a matrix. Now let A be an m by n matrix. That means matrix of the order n by m by n. Then transpose of A is defined as that matrix which is obtained by interchanging the rows and columns of A. All right, and transpose of A is denoted as A raised to power T or A dash. Okay, this is a notation of transpose. So example, if A is a matrix 3 1 5 minus 2 0 minus 1, then A transpose is the first row becomes the first column for the transpose, and the second row becomes the second column. So row becomes column and column becomes the row. The first column becomes the first row, the second column becomes the second row, the third column becomes the third row. So columns and rows get interchanged. That is transpose. So here it was a 3 by 2 sorry, 2 by 3 matrix. This is 2 rows and 3 columns, and this becomes a 3 by 2 matrix. So let's say this is example 1.
Sir, what is that? I mean, above the example, sir, transpose of A is
Denoted, notation. We are transpose, we are representing as A to the power T or A dash. Okay, clear?
yes, sir, yes, sir.
Hmm. So in compact notation, so if A Aij to the power, sorry, M cross N, then A transpose or A dash will be equal to A Ji N cross N. Whatever is Ij becomes Ji. That means the jth column becomes the jth row here. Okay. Example 2. Let's take a 3 by 3 matrix. Hmm. Okay. This is um, this is a 3 by 3 matrix. Okay. Then transpose of A, or denoted like this, is what will the transpose be? Please tell me. The first column here is 2 minus 1 3. This becomes the first row. 2 minus 1 3. Then the second column is 1 0 2. That becomes the second row. 1 0 2. Then the third column becomes the third row. Minus 3 4 5. Okay. So this is the transpose of a matrix. Now transpose has certain properties. Properties of transpose. First one, A transpose, the whole transpose will be A. Transpose of A, again take a transpose of that. That will be A. Then K times A transpose. All right. K times A, the whole transpose, is K times A transpose. So transpose does not affect the scalar. Okay. Transpose does not act on the scalar. Now, A plus B, but if there are two matrices, A plus B, the whole transpose, will be A transpose plus B transpose. However, very important, AB whole transpose will be same as reverse the order B transpose A transpose. Okay, this is a very important one. AB whole transpose is B transpose A transpose, not A transpose B transpose. Why? Very simple. Say if A is of the order, okay, A is of the order m by n, and B is of the order n by p, then the product AB is of the order, tell me, what is the product AB of the order? M, forgot, m by n, n by p. So the product AB will be of the order m,
M cross P.
m cross p. Very good. Now AB whole transpose will be of the order P cross M, isn't it? All right. Now, if you do, what is A transpose? A transpose is of the order N cross M, and B transpose is of the order P cross N. All right. N cross P, it becomes P cross N. So now A transpose B transpose is not conformable. So A transpose B transpose is not conformable. Why? You cannot multiply. Product does not exist. Why? Because A transpose is of the order N by M. B transpose is of the order P by N. Now, for matrix multiplication, it's a must that the number of columns of M should be equal to the number of rows, the number of columns of the first matrix should be equal to the number of rows of the second matrix of the product. But this is not. So you cannot multiply. Okay, product does not exist. However, B transpose A transpose. This is B transpose is.
It will exist, sir.
Yes.
Because N and N will be cancelled.
Yes. Not cancel. It is like in the product, we don't say cancel. So you see, the number of columns of the first matrix will be equal to the number of rows of the second matrix. Then product exists, and the product is P by M. Okay. So this is what it is. So that is why A transpose B transpose has to be necessarily A B whole transpose is B transpose A transpose. Okay, this is a very important definition. So we can prove it. We'll take an example, numerical example. All right. We will take problems on this now. Let's say A is okay. Now A is 213054 and B. So number of columns is 3. So number of rows of B should be 3. So you have one, purposely I'll give a square matrix, or maybe I'll give there's a rectangular matrix. So this is row matrix, this is a column matrix type formation. Let us do this. Okay, this is the question. Find AB, all right, and show that AB whole transpose is equal to B transpose A transpose. All right. So let us find AB. So AB solution. Two, 1, 3, 0, 5, 4. 1, 2, 3, 4, minus 1, minus 2. Okay. So first row gets multiplied with first column. This is what 2 by 3, and this is 3 by 2. You will get a 2 by 2 matrix. So 2 into 1, 2, plus 1 into 3, 3, plus 3 into minus 1, which is minus 3. Next, first row, second column. So first row, second column element will be this. 2 into 2, 4, plus 1 into 4 is 4. Then 3 into minus 2 is minus 6. All right. Then next, second row, first column. 0 into 1, 0. 5 into 3, 15. 4 into minus 1, minus 4. Then last one, second row, second column. 0 into 2, 0. Plus 5 into 4, 20. 4 into minus 2 is minus 8. So we get 2. 4 plus 4, 8 minus 6, 2. Okay. And then 15 minus 4, 11. 20 minus 8 is 12. Okay. Now this is AB. Now let us find A transpose and B transpose. Now A transpose is, this is A. What is A transpose? Change the row to column. 2, 1, 3 is the row. Change it to column. 2, 1, 3. 0, 5, 4 is the row. Change it to column. 0, 5, 4. This is A transpose. A transpose has become 3 by 2. What is B transpose? The first column becomes the first row. 1, 3, minus 1. And second column becomes the second row. 2, 4, minus 2. So now let us do B transpose, A transpose. Now B transpose, A transpose is 1, 3, minus 1, 2, 4, minus 2 multiplied by 2, 0, 1, 5, 3, 4.
So should we find the product of this both the transposes, sir?
Yes, that is what. Now show that AB whole transpose is B transpose, A transpose. We have found AB. We'll now find AB whole transpose. Okay. Now this is 2 rows, 3 columns. This is 3 rows, 2 columns. Now the product will be 2 rows, 2 columns. Now let us start. The first row gets multiplied by first column. So 1 into 2, 2, 3 into 1, 3, minus 1 into 3 is minus 3. And first row, second column, 1 into 0, 0, 3 into 5, 15, minus 1 into 4, minus 4. Then next, second row, first column, 2 into 2, 4, 4 into 1, 4, minus 2 into 3, minus 6. And then second row, second column, 0, 2 into 0, 5 into 4, 20, minus 8.
2, 11, 2, 12.
Yes. 2, 11, 2, 12, which is same as, observe this. What is this is 2, 2, 11, 12. Transpose of this will give you 2, 11, 2, 12, right? Changing this first row to first column. So here only I can write AB whole transpose will be 2, 2, 11, 12. So 2, 11, 2, 12. So this is same as AB the whole transpose. Therefore, AB whole transpose is equal to B transpose A transpose. All right. Okay. Additions and other things we can do. Now, again, now they are matrices based on certain definitions, based on transpose. Earlier we defined matrices, classification of matrices based on structure. Now we have classification of matrices based on their properties. I'll start in a new fresh page. Classification of matrices based on algebraic properties. Some problem. All right. The first one, very, very important, very important, symmetric matrix. Symmetric matrix. What is a symmetric matrix? Okay. A is a symmetric matrix if A transpose is equal to A. If A transpose is equal to A, then it's a symmetric matrix. Example. Examples. The first one. This necessarily means it should be a square matrix. Otherwise, you cannot. If transpose m by n becomes n by m, you will not. So you get, 1, 2, 2, 4. This is an example of a symmetric matrix. So A transpose is also take the first row and make it into first column. Take the second row, make it into the second column. You get the same result. Why you get the same result? Because the off diagonal terms other than the diagonal, the elements are identical. All right. Now let's look at a so here this is A transpose is equal to A. Now let us look at 3 by 3. A is 1, 5, 7, let's say, and then 0, -1, 2, 0, -1, 2. Okay, what have we done? You observe here. When you just observe, you should be able to tell it's a symmetric matrix. Why? Because you don't have to do an operation. You, apart from the principal diagonal elements, the other elements are symmetrically mirror image situated. So it's a symmetric matrix. So therefore, A transpose, if you do, take the first row, make it into a first column, or first column, you make it into a first row, doesn't matter. First row, I make it into the first column. The second row, I make it into the second column. The third row, I make it into the third column. Still, you get identical matrix. So A transpose is equal to A. All right. Now in compact notation, A equal to Aij n cross n, it has to be a square matrix, is symmetric if Aij is equal to Aji. Aij is equal to Aji for all I not equal to j. So A23 will be equal to A32. So A23, 23 is second row, third column is 2. A32 is third row, second column. Third row, second column. So in compact notation, so Aij is symmetric if this condition is valid. All right, so this is a symmetric matrix. So an important property associated with this result. Note, if A is a square matrix, then A plus A transpose is a symmetric matrix. It is a symmetric matrix. Proof is very simple. A plus A transpose whole transpose is nothing but A transpose plus A transpose whole transpose, the property, which is A transpose plus A, because A transpose whole transpose is A, again a property. And because matrix addition is commutative, so this is A times, this is A plus A transpose. So A plus A transpose whole transpose is A plus A transpose. So A plus A transpose is a symmetric matrix. Very important result conceptually. Next, second result is skew symmetric matrix. Skew symmetric matrix. Skew symmetric matrix. So if A is a square matrix, such that A transpose is minus A. A transpose is minus A. Then A is called as a skew symmetric matrix. Okay. Now, first I'll explain. Achha, when you do a transpose, you observe here, even if a matrix of the size 3 by 3, you see the diagonal elements above, when you do a transpose, the diagonal elements will not change. 157 remains 157, 14 remains 14. No matter, not just for this problem, but even for the previous problems, when we did transpose, you can see when you do transpose, the diagonal elements will not change. Here, the previous problem, 205 is the diagonal elements. Diagonal elements remain at the same location, because what is transpose? Row become column, column become row. So Aij becomes Aji. Okay. However, when for these principal diagonal elements, the term is AII, A11, A22, A33. All right. So when you transpose it, the transpose of it will again be AII. It will be again at the same location. So the diagonal elements will not change their location during a transpose. So now comes an important catch for skew symmetric matrix. Now A transpose is minus A. Can a number be equal to, so think about the diagonal elements. Can a number be equal to its own negative? Is it possible? Is it possible? No. So now, if this is not possible, then what is that number when you take its negative, which it will be equal to the original number? Tell me. It is only possible if that number is 0. Any other number other than 0, this equality will not hold. Understand? So therefore, skew symmetric matrix have a pattern. You see, example. Now A is, you observe this, the diagonal elements I am writing 0. And then look at this, 1 minus 1, okay, 2 minus 2, so 5 minus 5. So just look at how the skew symmetric matrix looks. The diagonal elements will be 0. Across the diagonal elements, the numerical values will be the same, 1 1, 2 2, 5 5, but they will be of opposite signs. They will be of opposite signs.
Sir, the same pattern will be given, everywhere in this matrix, or the pattern will change?
This zeros is a must. For a skew symmetric matrix, the
That's
diagonal
okay.
elements will be 0. Now
But
it can be plus minus, can
But
be
all
other way,
skew
right?
symmetric matrices only zeros, right, sir? Principal
Yes,
diagonal.
yes, principal diagonal will be 0. So now you do transpose. Let us see, when you do transpose, what do you get? 0 1 2, the row becomes column. 0 1 2. Then minus 1 0 minus 5, the second row becomes second column. Minus 1 0 minus 1. Then third row becomes the third column. Minus 2 5 0. Okay, now what do you get? This is same as multiplying a with minus 1. So this is minus 1 times, you take the minus sign outside, minus 2 5 0. This is same as a, right? So A transpose is equal to minus A. That means it's a skew symmetric matrix. We call it as a skew symmetric matrix. So in compact notation, if A is a square matrix, A I J n cross n, then and okay, such that Aij is equal to minus Aji. Okay, for all I not equal to j, and Aij is equal to 0 for all I equal to j. Then A is a skew symmetric matrix. Then A is a skew symmetric matrix. So symmetric matrix, skew symmetric matrix. All right. There are other notations also. I'll just show. I'll teach a little bit beyond the syllabus. It's a must because this is a very critical and important chapter. Symmetric, skew symmetric. There are so many properties of symmetric and skew symmetric. Orthogonal. Okay. I have to teach A inverse for this. All right. So note here property that A minus A transpose is a skew symmetric matrix. A minus A transpose is a skew symmetric matrix. Proof is very simple. A minus A transpose, the whole transpose, is nothing but A transpose minus A transpose, the whole transpose. That's equal to A transpose minus A, which is minus of A minus A transpose. So you get A minus A transpose, the whole transpose, is minus of A minus A transpose. So by definition, this is a skew symmetric matrix. Okay. Next, the definition is of very important, this orthogonal matrix. Okay. A is called an orthogonal matrix if A multiplied by A transpose is equal to A transpose multiplied by A is equal to I. Okay, this is called as an orthogonal matrix. The most basic of orthogonal matrix is this: cos theta minus sin theta, sin theta, cos theta. A. All right, this is a basic. A transpose it will be cos theta minus sin theta, sin theta, cos theta. Now A into A transpose, if you do, you will get first row multiplied by the first column. You get cos square theta plus sin square theta. Then the second term is first row multiplied by the second column. First row, second column. So you get cos theta sin theta minus sin theta cos theta. Then next, sin theta cos theta sin theta. The second row, first column. So I get sin theta cos theta minus cos theta sin theta. And the last one, you get sin square theta plus cos square theta. So you get sine square theta plus cos square theta is 1. This term is 0. This is 0. This is 1. This is identity matrix. So A into A transpose is equal to I. So A is orthogonal. So A is an orthogonal matrix. Okay. Next. Then you have orthogonal matrix. Then you have a few other definitions. Idempotent matrix and involutory matrix, nilpotent matrix, singular matrix. There are more, of course, there are matrices that use complex numbers. So they have certain terms. All these Hermitian, skew Hermitian, and all these things, I will teach you. Hermitian, skew Hermitian, unitary. I'll be teaching you when I'll do second year, but at least symmetric, skew symmetric, orthogonal is all right. Idempotent, involutory, and nilpotent. These three we'll teach now. Idempotent matrix. Okay, what is an idempotent matrix? A square matrix A is said to be idempotent if A square is equal to A. So if A square is equal to A, then A is called an idempotent matrix. Next, involutory matrix.
Sir, application problems.
Yeah, I'll show.
Okay, sir.
Involutory, you'll have to involutory if A square is equal to I, then A is called an involutory matrix.
Sir, what is I, sir?
I is identity matrix.
Okay, sir.
Anything you multiply with I, A into I will give you A.
Sir, for idempotent matrix, is it only A square or A power anything
No,
is also possible?
no, A square only. It is only A square. For idempotent matrix, the definition is A square.
Identity matrix acts as one, right, sir? I mean unitary.
Yes, that's why it is called as
Okay.
identity matrix.
Okay, sir. Okay, sir.
Okay. Then there is nilpotent. Nilpotent matrix of a particular order. Okay. If A power m becomes 0, if A power m becomes 0 for least positive integer value of m, then A is called a nilpotent matrix of order m. Okay, is nilpotent matrix of order m. So a square equal to a. I'll have to. So let us find examples for this. We'll create examples. So a, let us say a is x, y, u, v. Now a square will be x, y, u, v multiplied by x, y, u, v. So you'll get x square plus uy. Then okay, then next you get xy plus yv or vy. Next you get xu or ux or xu plus uv, or and last you get
Sir,
mm,
instead of x square, we have to get y square, sir.
why?
Because we are multiplying this xy with this diagonal, no, sir. Xy
No,
into y v.
xy into yv. So you get x multiplies by multiplies with y,
Yeah,
y
yes, sir, yes, sir,
multiplies by
yes.
v.
Yes.
Okay. So u multiplies by y, v multiplies by v. So this is a square. Now for this to be idempotent, a square equal to a means this is equal to x, y, u, v. So you will have to see what we can do. So basically x square plus uy is equal to x. This is the first term. The second term will be take y common, x plus v times y is equal to y, which implies x plus v should be equal to 1. Third one, take u common, x plus v, u times x plus v is equal to u, which implies x plus v should be 1. We are trying to find out which are the idempotent matrices. It is not just easy to just frame a idempotent or involutory matrices. Symmetric, skew symmetric, any matrix I can take and do, but this will follow certain rules. So x, uh, you can get, so x plus v, x plus v should be 1. So x can be 0, and then v can be, let us try, 1001 will definitely be one matrix. Okay, one basic matrix is A is 1001. This is identity. This will hold true for all cases, doesn't matter. I am saying other cases. So now let us try put x equal to 0, then v should be equal to 1. So this term you will get 0, 0. So this term u into y has to be 0. U into y has to be 0. So 1 of u and y should be 0. Now come to this term. All right. The second term, put no, and sorry, uy plus v square is equal to v, which implies v is 1, so 1 1 cancel, so again uy is 0. Okay, uy is 0, same thing. So either u is 0 or y is 0. So then you can now formulate a matrix. So A is x, y, u, v. X is 0, v is 1, that is fixed. Now either of them can be 0. So let us put this as 0, this as 2. So A is 0, 0, 2, 1. A square. Let us see whether it works. So A square, first term 0, 0, 0 multiplied by 0 into 2. So 0 plus 0. Second term 0 plus 0. Third term 2 into 0, 0 plus 1 into 2, 2. Last one 2 into 0, 0 plus 1 into 1, 1. So you get 0, 0, 2, 1. So A is an example of an idempotent matrix.
So could you again once again explain how did we get u to be 2 and v to be 1? So
No, I can assume 2, I can assume 3. See, I get
okay. It's the
either
assuming value.
either I want to find out all the idempotent matrices. So there are many combinations. The first combination you have to get is x plus v is equal to 1. So you can get x equal to 0, v equal to 1, or x equal to 1, v equal to 0, so on. Okay. So you wanted me to give an example of idempotent matrix, right? So off the shelf, it was not in my mind. So I created. How I created? By logic. Now I will change it. See, I will put y as 0. So y was 0, u was 2 here. Now I'll make u as 0. So 0, 1. Okay. 0, 1. And now y I'll make as 5. And this becomes 0. So what happens to a square? 0, 0, 5, 1. 0, 0, 5, 1. When you square, the first row gets multiplied by the first column. The first row gets multiplied by the second column. 0 into 5 plus 5 into 1. The second row gets multiplied by the first column, 0 plus 0. The second row gets multiplied by the second column, 0 plus 1. So again you get 0, 0, 5, 1. So this is also an example of an idempotent matrix. Okay. Same thing we can extend to involutory. We can find out like this. So for idempotent matrix, one row or one column will be 0. All right, and the sum of the diagonals here is 1, like for 2 by 2. All right, I'll stop here. I'll continue tomorrow with this. More properties of matrices. Then I have to start determinants. Then I have to teach you inverse. All right.
Sir,
Yes.
I have a few doubts in this chapter's questions.
Which chapter? Today's.
Yeah, today's chapter, matrices.
Okay. If you don't mind, can we do it tomorrow? Because I actually have a
Can you also like forward, like tell me your number and note it down so I can like send you the questions and I can like remember.
Sure. Okay. If you register, you will be on the group. You can put on the group also. But my number is.
I'm not in the group.
So I'll put you. You send me your number. My number is 7981705530.
Okay, I'll note it down too. I'll note it down.
7981705530.
Yeah. Okay.
70
70.
5530.
Okay, yeah, got it.
Okay. All right.
Sir, one more thing. I got a mail that about the login and password.
Yes.
So, but there are not any like assignments are not given. So.
Okay. Because you have to be added to a particular course. All right. I'll do that. Okay.
Okay.
I'll do that. Yesterday, I think.
Even I need a login password.
Yeah. If have you see, Prisha, if login and password is created only when you give the deposit. That's the policy, and I give it to another friend of mine who maintains that website, Moodle website for me. All right.
Oh,
So
yes, sir.
okay. So as soon as you pay the first deposit, and then immediately login and password will be generated.
Okay, sir, I'll do that.
Okay. Yes, Astuti, you have a question?
Yes, sir. Did you get the opportunity to look at the questions I sent you?
Yeah, I looked at the questions, just that I was packed yesterday.
Oh, okay.
Really? Okay. I will definitely, you in my mind, I have been delaying you quite a bit. I'll do that tomorrow evening, if you don't mind, right after class between 6:15 to 6:45. I'll take your questions.
Okay, sir. Sure.
Okay. Okay.
Thank you.
Thank you. All right.